boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to the Naked Scientists with me, Diana O'Carroll.
And me, Meera Lingam.
This week we've taken over from the other boys and girls at the Naked Scientists to bring you our favourite naked science. Plus we've got the next explosive set of experiments from the singular Dr. Hal and Sideshow Dave.
Coming up, we take a trip, literally, into the stratosphere with some parajetting over some very high mountains.
Once you're up in the air, you've got to keep the finger on the throttle. You've got that little hand control, and you squeeze that hand control, and that keeps the engine revved up, and you keep being blown higher and higher and higher. Now, when you get to the maximum height you want to go, you can switch off your engine, and the wing keeps flying, so you can just glide back down again. So what we did, we flew to 30,000 feet, switched off the engines, and glid all the way back down to our starting point.
We also find out how ancient pieces of pottery are without the use of that staple technique, carbon dating.
I think the problem is that most people think that carbon-14 dating can be used to date anything. And in fact it can't. It can only be used to date things that have been living. Now our method is self-calibrating and doesn't require any material from around the excavated site. So we can actually use it retrospectively on a lump of clay or a lump of pot or brick or whatever that's been sitting in a museum.
And Chris meets a sword swallower to find out just how they do it.
He's going to do it. Oh my god. It is right the way down through his back of his throat and down into his stomach. And there's no blood on it either, which is a good thing, because we don't actually... I might be a doctor, but I didn't have a first aid kit, which is...
Very good.
Don't try that at home, kids. So we've got some exciting stuff coming up on today's show. But if you'd like to get in touch with us with any questions or comments about our choices this week, then why not drop us an email with the address chris@thenakedscientists.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Our first choice this week is from a group of adrenaline-seeking adventurers who thought it would be a great idea to parajet over Mount Everest.
Something I have to admit I was very jealous of, Diana.
You're not the only one. They did this back in 2007 when Meera met up with Giles Cardozo, Bear Grylls and Michael Vore to find out how they came up with such a crazy idea, and more importantly, how they made it happen.
Imagine what it would feel like to fly. And if you could fly, what would it be like to fly over something like Mount Everest, the tallest mountain in the world? Well, thanks to the new sport of paramotoring, which uses parajets to elevate you into the air and then paragliders to bring you back down, not only are people able to live the dream of personal flight, but two Brits have managed to break the world record for the height reached using only a parajet. In May this year, Giles Cardozo and Bear Grylls flew above the summit of Mount Everest and reached a height of 30,000 feet. The challenge was known as Mission Everest and was sponsored by technology company GKN. Now, the equipment they used to accomplish this mission was recently displayed at the Science Museum, London. So I went along to see how it all worked and find out just what it took to break this world record. I spoke to Giles Cardozo, who not only flew up the mountain, but also designed the equipment they actually used to get them up there. So I had to start by asking him just what a parajet actually is.
Well, a parajet is an aircraft that you wear on your back like a rucksack, and you have a paraglider wing, which you attach onto a harness, and using the thrust of this engine on your back with a propeller fitted to it, it blows you into the air, and the wing gives you the lift you need. Together you've got a complete flying machine, and you can fly up to 40 miles an hour, up to thousands of feet. In this case, we flew to 30,000 feet with it.
People do this for social purposes as well, so what kind of heights do they do if they're just doing this for fun?
Really, the highest you go is about 5,000 feet, just sort of above the clouds, so you have a nice view. But 15,000 feet, even that is the maximum altitude you could go to with a normal machine, but people never really go that high.
So what was involved in creating the equipment to take you that extra 15,000 feet?
Well, the most difficult thing really was making an engine that would still breathe where there's no oxygen, or very little oxygen. And at 30,000 feet, there's only a third of the oxygen in the air. An engine needs oxygen to run. That's what gives it its power. So we had to make a system that would drive an enormous amount of air or oxygen into the engine to make it produce enough power to keep us flying.
Well, how did you actually manage that? What kind of detail did you have to pay attention to when designing?
The most important thing was the fuel delivery, which is computer controlled, and the supercharging. The supercharger basically is like a little tiny impeller which whizzes around incredibly fast, and we got it spinning at 3,000 times per second. You can imagine that's rotating very, very quickly, and that would blast enough air into the engine, and now the computer then controlled the fuel delivery, and between the two of them, we managed to keep the engine running and propelling us into the air.
When actually doing the flight itself, you're using the engine to propel you, but then you essentially switch it off and use the winds.
Well, yes, once you're up in the air, you've got to keep the finger on the throttle. You've got that little hand control, and you squeeze that hand control, and that keeps the engine revved up, and you keep being blown higher and higher and higher. Now, when you get to the maximum height you want to go, you can switch off your engine, and the wing keeps flying, so you can just glide back down again. So what we did, we flew to 30,000 feet, switched off the engines, and glid all the way back down to our starting point.
And at heights like that, the actual person himself must need extreme protection to protect their own bodies.
Yeah, we had a wind chill factor of about minus 70. We had 3 layers of clothing on board, a whole load of underliners as well, and we had oxygen systems. We'd really pass out under a minute at 30,000 feet if we didn't have oxygen with us. And then a big helmet with about 2 balaclavas on. We had all the kit on to make sure we kept nice and tasty inside our kit.
The amount of power that the actual engine must need to take you up, I mean, it's 100 horsepower. Could you compare that to something just so people can get an idea of just how much power that is?
Yes, I mean, your average family car produces maybe 80 to 100 horsepower, and that's a sort of 4-6-seater car. Now, we had the engine equivalent power strapped to our backs, and yet it weighed 10 times less. That was the most difficult bit, was getting an engine to produce nearly 100 horsepower whilst being able to wear it quite happily on your back, and then carry enough fuel with you and everything else. So you realise how light the engine had to be to make it possible to actually make it work at all. If we added up everything, including fuel, all our helmets, electronics, the whole lot, we weighed about an extra 80 kilos, so more than my body weight on a back. I think I was fitter before I did this trip than I'd ever been in my life, yeah.
And what did it feel like to be at such a height?
Well, I think I dreamt of this moment for such a long time. Obviously, I was very excited, but also you feel very vulnerable because you're there amongst these huge mountains, miles and miles from anywhere. I think I was scared, but I was also very, very excited. And just an incredible view, really. To top it off, it was just staggering, yeah.
Giles's flying partner was adventure man Bear Grylls, who must have been facing some personal demons in this mission, having broken his back in 3 places in a previous parachuting adventure. I asked him how it felt to be hovering over the tallest peak in the world.
I always thought, God, I wonder if it's going to be really, really terrifying just being suspended in these little strings. But it just felt the most meant-to-be magical, extraordinary, privileged moment. And even though it was minus 40 degrees and you're so dependent on this one little oxygen canister for keeping you alive and you're aware you're at your most vulnerable point, there was something I think we both felt that this was really meant to be and what a privilege. And we'd had screaming winds for days, 100-mile-an-hour winds, massive snows, and we just had this 3-hour window of absolutely still weather all the way up to 30,000 feet. And to get still winds at 30,000 feet is unheard of. You speak to any pilot, you always have at least 80-mile-an-hour tailwinds or headwinds. And it all came together for those 3 hours, of which we did feel the luckiest men alive.
I can't even begin to imagine the physical endurance required to survive at such a height, let alone having to control something that's suspending you in midair. To get you thinking about how high Mount Everest actually is, and therefore how high in the air the duo were flying on their own, I'll leave you with this comparison from Michael Vore, a member of the GKN team.
When you think about it, 30,000 feet is the height of an aircraft flying. So when you go on your holidays and you're flying at that type of feet, you imagine looking out of the window and seeing a guy in a parachute basically flying past you. It's quite a challenge.
Michael Vore there, talking to Meera and some anoxic flying from the daring pilots. I don't know if I own any underwear thermally insulated enough to cope with 30,000 feet.
No, me either. Definitely not.
Keeping you abreast of the world's best science. The Naked Scientists.
This is The Naked Scientist with Meera and Diana. Now, while talking of things thermal, here's a story on fired clay. Now, normally ancient bits of pot and brick are dated using carbon samples or thermoluminescence, but these techniques require lots of sampling and calibrating, which takes time. So it was quite a surprise when construction scientist Moira Wilson came up with a really simple method of dating ceramics.
I think the problem is that most people think that carbon-14 dating can be used to date anything. And in fact it can't. It can only be used to date things that have been living, like, plant material, bone, or whatever that's been exchanging carbon with the atmosphere throughout its lifetime. So you can't carbon date everything, that's the first thing. And you certainly can't carbon date pottery. Thermoluminescence that can be used to date pottery, this is actually quite a complicated thing. You need to excavate quite a large volume of material from around the fragment of pot during the archaeological dig, because you need this material to get a background count for calibration. And thermoluminescence is calibrated against the carbon-14 dating curve. Now, our method is self-calibrating and doesn't require any material from around the excavated site. So we can actually use it retrospectively on a lump of clay or a lump of pot or brick or whatever that's been sitting in a museum.
And how did you go about discovering this technique, and what gave you the inspiration in the first place?
Right, well, it sounds a bit of a weird thing to do, but they say that chance favours the prepared mind. What we were actually working on at the time was moisture expansion in clay masonry. And this is an engineering problem, really, in masonry construction, that bricks expand. Okay, this is why you have expansion joints in walls, for example. So as soon as the bricks come out of the kiln, they start expanding and carry on expanding forever. And this is why in general practice, bricks would never be used straight from the brickyard. They'd be left for a few days. So we started off looking at the engineering problems.
So basically you were trying to find a way of being able to predict how these bricks would behave after they came out of the kiln.
Yeah, what we were looking at was moisture expansion in clay brick, as in walls. In the process of doing so, we discovered a new law, and we found that these materials expand at a rate that's proportional to the fourth root of time. For example, if you have a kilometre of wall that's about 200 years old, it will, in the course of that 200 years, expanded by about a metre.
Wow.
Yeah, but that doesn't mean the wall gets longer by a metre, because what happens is that the expansion of each individual brick is accommodated by the mortar joints getting squashed up.
All right, then, so what are the actual particulars of the technique that other archaeologists could do themselves eventually?
Right, so how it works. Well, as I say, the dating method relies on this new law, but fundamentally what it relies on is that as soon as any fired clay product is removed from the kiln, it starts gaining weight and expanding, caused by the reaction between the ceramic and atmospheric moisture. And this, as we say, carries on forever. So if we take the example of a whole brick, we would weigh the brick, first of all. And the weight now is its original weight as it came out of the kiln, plus the weight of the chemically combined water that's reacted with it over its lifetime. Then we heat the material to several hundred degrees to drive off this chemically combined water, and then we weigh it again. So we can establish from that how much water it's gained over its lifetime. And in the case of a Roman brick, say, that would be about 40 grams. So once we've driven all this chemically combined water off, it starts to recombine again. So it starts all over again. So we monitor this for a few days, and it obeys our T to the quarter law, so the data come out as a nice straight line. And from this, we can establish the rate at which the material is reacting with water. And if we know how much it's lost, we can work out how long it's going to take to gain that much water again.
So each measurement is specific to a different type of ceramic?
It is, and it's self-calibrating, so we don't need any other external calibration data for it at all. It doesn't matter what the sort of clay it's made of or anything, and it's very simple, you see.
Can sort of ambient humidity change the result at all?
Nope. This is the other nice thing about it. This chemical reaction is incredibly slow. It's proceeding in increments of 1, 16, 81, 256 minutes, days, decades, whatever. So the reaction rate, very fast to start with, it slows down very, very quickly. And the reaction is sustained by an incredibly small quantity of water. So there's actually sufficient moisture in the atmosphere to keep the reaction going. So it doesn't actually matter whether your brick is sitting on the table or it's sitting at the bottom of a lake. As long as there's enough water there to sustain the reaction, any excess water, for example, if the material is saturated, it doesn't contribute to the reaction, it just sits there doing nothing.
OK, and how accurate are the dates, do you think, that you could get from, say, a bit of pottery that's maybe something around 2,000 years old? I mean, how accurate, if it was that old, would your date be?
Well, I think the biggest inaccuracy that we've got in our results is the supposed known age of the sample in the first place. I mean, we don't know that a brick was fired on the 5th of July at 2:30 in the afternoon or something like that. We just know it's Roman, for example. So if we can date a Roman brick to 2001 years, that's great. It's certainly in the right ballpark. But as far as the magnitude of it goes, say we're looking at a Roman brick, we don't measure whole bricks, we measure 4-gram pieces. So in the course of 2,000 years, say, we'd expect a 4-gram piece to have gained about 68 milligrams in mass. Now, if we're measuring to 1/10 of a millionth of a gram, that's actually a lot of units of measurement that are available to us. So really, I suppose what you're saying is how accurate are all the components of this? The mass measurement is virtually error-free, we would say.
Fantastic. You mentioned there that you used a 4-gram sample as like a starting point, but is that the smallest you can go to, or could you take a really small scraping and work from that?
Well, actually, given that we started off measuring the mass gain in whole bricks, which is about 2.5 kilograms, and then we moved down to 4 grams, which is about half the size of a sugar cube, and now we're down to milligram-sized pieces. So we're getting the sample size down all the time, which is an advantage.
Wonderful. And apart from archaeology, how else could this technique be used?
Well, because the mass gain in these materials follows this precisely defined kinetic law, and because it's also temperature dependent, we could, if we knew the precise date at which something was fired, and there are instances of this, like Pompeii, for example, was immersed in pyroclastic ash in AD 79. So we know the precise date at which all the ceramics in Pompeii were heated up. We could then turn the method on its head, and because we know the exact firing date, we could work out the average temperature that the material had been exposed to over this precisely known lifetime. So there might be a bit of climate change potential there as well.
So what's the next stage in researching this technique? Are you going to apply it to objects you know the date of first, or are you just going to sort of have a play and see if you can debunk any other previous dates that have been taken on pottery?
It's gone beyond having a play, really. We've had this fantastic or overwhelming international response from the archaeological community to this work. I mean, we're really shocked, actually. So the next stage of the work, really, is to validate the method. I mean, I suppose you could say we have already validated it. We've proved the concept. What we need to do now is to work out a standard methodology for carrying out these measurements, so that other people can do it. We also need to extend the time range of the samples that we've measured. We've only measured things to 2,000 years old so far, so we'd really like to look at some older samples. And we've heard in our correspondence with archaeologists that pyrotechnology apparently goes back to 16,000 BC. So if we can't get our hands on a piece of pottery that was 18,000 years old, we'd be really happy.
It seems too good to be true, and the team were actually thrown to start with, as they were given this medieval brick to test their theories on, and they just couldn't work out why the date came out at around 1939, but it turned out that the house in which the bricks had been stored was bombed during the Second World War, so the brick itself was actually refired, giving a much more recent date. So you might not want to use this method on the bricks at Pompeii.
Lifting the lab coat on the world's best science. The Naked Scientists.
This is The Naked Scientists with Meera and Diana, and this week we're bringing you our favourite bits of naked science. Still to come, we go back in time and investigate the world of ancient Greek brothels. Indeed. Plus, we blow up an ostrich egg. But first, we do a very important experiment, in my opinion, to find out how to make the perfect cup of tea. Now, Diana, how do you make your tea?
Actually, I don't drink tea. I can't stand this stuff. So when I make it for other people, I've got no idea what it tastes like, I'm afraid.
In which case, your opinion really doesn't count here. Now, I like to leave the bag in for a while, but the big question is, when do you add the milk? So we set Ben and Dave on the case, together with Chris, to find out how to get the hottest cup of tea.
This guy got in touch with me this week, and that's Bob. He's in Canada. Hi, Bob.
Hi.
Thank you for calling us up. You listen to The Naked Scientists in Canada?
Yes, I actually, I love listening to it. I just was in a bit of a time warp, though, because I listened to a show yesterday, and it turned out to be your Christmas 2005 show. So I have a long ways to go before I'm caught up.
I thought the time difference between here and Canada was only about 5 hours, Bob.
Well, I guess maybe I'm just in warp time.
So anyway, what was the question you would like us to look at for you?
Well, in the work that I do, I'm quite often interrupted for 10 or 15 minutes to go do something, and then I get back to my desk. And inevitably, when I'm making my cup of tea, before I get finished, I'll be interrupted again. So my question is, I've made my tea, and I'm just about to put my cream into the tea, or my milk. And my question is, if I want my tea to be as hot as possible when I finally get to drink it, should I add the cream right away, or should I wait and add it just before I drink it? Which way will give me the hottest tea in the end?
Well, Bob, I plan to do an experiment today live in the studio and try and find out what is the answer to this question. So what I've got 3 identical mugs, and I've got a nice pot of tea, so I'm going to pour out tea into all these 3 mugs.
It really has. I've never seen him use a teapot. Dave's normally so uncivilised, and it's actually got a really nice brew coming out.
So I'm going to try and pour about the same amount of tea into each cup, which will involve pouring some out of that one. So having a nice even amount of tea in each. Then good. One of them I'm going to add milk to now and stir it in nicely. The other one I'm going to wait until the end of the show when I'm going to stir in some milk at the end. And the third one, I have a sneaky suspicion. What I'm going to do is I'm going to add some cream and just leave it on the surface. So I'll do that. I'll add some cream to one of them now.
Is this a cholesterol poisoning test on the side, Dave, or something?
Well, it keeps me amused.
Well, why are you doing this with the cream?
Well, I have a sneaky suspicion that if I can pour it onto the top and so it sits on the top, I might be able to act as an insulating layer on the top.
So the fat will float to the top. So you think cream... We're going to do wonders for people's arteries on this programme if they all start adding cream to their tea to try and keep it warmer.
Well, I apologise if I cause many people to die of heart disease.
Okay, so Dave is now adding equivalent amounts of milk and stuff to each of these things. So, Bob, are you impressed with the scientific technique being employed by Dr. Dave on The Naked Scientist?
Oh, it's a lot better than what I've been trying to do.
Well, look, we're going to now do this scientifically through the programme. If you would be so kind as to rejoin us at the end when we take the final temperature measurements, we'll tell you what you should do in your workplace with your cup of tea to make sure you have the warmest beverage.
I do just love a good cup of tea. Your opinion doesn't count. And we'll be coming back to that highly scientific experiment later on in the show. But now let's rejoin Chris for something slightly less palatable, and that's sword swallowing.
My name is Dan Meyer. I'm the president of the Sword Swallowers Association International. I was honored to receive the Ig Nobel Prize in Medicine last year for a paper that I co-wrote called Sword Swallowing and Its Side Effects that was published in the British Medical Journal.
And what are those side effects?
Well, one of them is death. We know of 29 sword swallowers who have died of sword swallowing injuries or sword swallowing related injuries. Other side effects are what we call sword throats. You get that when you begin learning sword swallowing, a lot of sword throats.
Different from a sore throat?
Well, no, about the same thing, but you put a D on the end of it and it sounds better.
So, anatomically speaking, when you swallow a sword, you are quite literally inserting something straight from your mouth straight through into your stomach, are you?
Exactly, all the way down. But people think it's just a simple repress the gag reflex and that's it. That's really just the tip of the iceberg.
Or the tip of the sword even.
The tip of the sword. You have to repress the gag reflex at first, then you have to flip back your epiglottis in your throat, repress the peristalsis reflex, which is 22 pairs of muscles that swallows your food all the way down to your stomach, nudge your heart to the left, then relax your lower esophageal sphincter just before it goes into the stomach, then repress the Retz reflex in the stomach. So there's a lot to it.
And when did you start doing this?
I started learning in 1997. It took me 3 years of practice. It takes most people 3 years to 7 years to learn how to do it and another 5 years to master it.
When you say learn, as in learning to switch off all those reflexes, there's something going the wrong way down my gullet and it's hard and it's long and it's a sword.
Yes.
How do you learn? This isn't self-taught, presumably. It's not something you do in front of the bathroom mirror.
Actually, it is self-taught. Almost everybody has to learn to do it themselves. Sometimes people will get a mentor that will teach them, but you really, even if you have a mentor, you still have to do it yourself. You have to learn the mechanism inside the body to flip the epiglottis closed and do all that type of thing.
What possessed you to write this paper that got you the Ig Nobel Prize?
Well, a serious injury, actually. I had punctured my stomach while I was swallowing 5 swords at one time. And as the president of the Sword Swallowers Association, I knew all the sword swallowers worldwide. But when I realized there was very little medical information in the medical journals or any of the medical books, I said, we've got to research this so that the doctors have someplace they can turn for help. The results of our study was that nearly each of us has at least one serious injury at some point or another. You do this long enough, it's like Russian roulette. You will get hurt. But one of the other things we learned, curiously enough, is that for most sword swallowers swallowing a single sword, you don't have that many injuries, comparatively speaking, until you start doing something unusual, like swallowing multiple swords. In my case, I was swallowing 5, 6 swords with a macaw on my shoulder. She climbed on the back of my neck, started climbing down my collar. I turned my head while I had 5 swords down my throat, and it pinched something, and I had a little scissoring in the stomach, and it was about cost me my life.
When did you realise that that was a pretty serious injury? Was it pretty immediate?
It was immediate. It was a pain in the chest, and sometimes when we get that, it's kind of some bruising and muscular bruising type thing. A lot of times if you drink a lot of cold ice water and let it go for a few days, sometimes it'll heal itself. In this case, it was okay for about a week until a week later, and I was swallowing 5 swords again, and my stomach retched upwards, and that time I knew it. And I ended up going to the hospital. I had fluid around my lungs, my heart. I couldn't breathe. My heart couldn't beat very well because it had so much fluid around it, and it almost killed me.
And have you presumably returned to the art since then?
I did exactly a month to the day. I had a film shoot that I had to do, and I did it, and I've been back in the saddle ever since.
Is this your full-time occupation? Is this how you earn your money?
It is. It's my full-time occupation. Actually, it's also my passion. I absolutely love sword swallowing and studying it.
What did you do before you became a sword swallower?
I actually worked in the music industry in Nashville, Tennessee for about 20 years. Then I got married, moved to Alabama, and was selling cars for a few months and absolutely hated it until my manager said, "You've got to do something to make the car sales very memorable." And I said, "Oh, I can do that." And so I offered to swallow a sword anytime somebody would buy a car from me. And it became famous in all the papers and all around the United States. And it was a lot of fun, and it kept me in practice too.
And now you do it professionally. Will you do it professionally for me today?
Possibly, yes. Now, what I have here...
Beautiful.
It's a 30-inch silver sword. You can feel it's a bit heavy on the heavy side.
This is no trickery. This is a real sword.
Yes. There's no buttons. Nothing will fold up in the handle. This one will go down to about my belly button or to my belt buckle.
Yeah.
But it's solid steel. And what I'm going to do is flip back my epiglottis, slide it down my esophagus all the way down to my stomach here for you. So I'll let you narrate this as it goes down.
Okay, so what he's now doing is licking the blade with his... It's actually got the sword in his mouth, running it sideways across his tongue to lubricate, presumably.
To lubricate it, also to feel for nicks and burrs, and also to warm up the blade. It's a little chilly from being outside.
Okay. He's going to do it. Oh, my God. It is right the way down through his back of his throat and down into his stomach. And there's no blood on it either, which is a good thing, because we don't actually... I might be a doctor, but I didn't have a first aid kit, which is...
Very good.
So when you do your talk for the Ig Nobel tour, which is taking place at the moment, what will you be saying to people? Obviously, don't try this at home, but
right.
But what's the point you're trying to make?
Well, one of the things that I do is try to prove to people that sword swallowing is real, because a lot of people don't believe it's real. They think it's died out. It's a 4,000-year-old art. It started in India about 2000 BC. But we also go through and describe our paper, the findings of our paper. And the Ig Nobels are set up to make people think and to make people smile, or make people smile, make people laugh, and to make them think. And so we do a little of both. You know, you think, what? A paper on sword swallowing injuries? Of course people get injured. But then when you see it and understand it, people go, oh my gosh, that is real. That's fascinating. And it's a lot of fun.
Dan Mayer speaking to Chris Smith about the risky art of sword swallowing. Meera, have you ever wanted to join the circus?
Well, I can't say that I have, and listening to those near gagging noises from Dan there, it hasn't really convinced me. I have to admit that's quite a talent, though. You?
Only food goes in this mouth, Meera.
That's not what I've heard. Anyway, it's now time to look into, well, another form of entertainment, I guess, as we go back in time to ancient Greece to learn about their brothels.
It seems that over 2,000 years ago in the classical world, pubs, brothels and prostitution existed as they do today, but not quite in the same capacity. It turns out that charity was not the only thing to start at home, but that brothels and drinking dens also occupied rooms of Greek houses. Claire Kelly-Blaseby believes that rather than having separate buildings for such entertainments, instead Greeks would host the fun in their own front room.
Well, my research focuses on the archaeology of casual wine consumption in classical Greece, so the architecture and material culture of bars and other non-elite drinking contexts. I couldn't understand why, when we unearthed so many drinking cups on excavations of classical sites, that nobody was attributing them to tavernas. There was plenty of talk about ritual, public and domestic or sympathetic drinking. These are usually always discussed, but bars weren't, and I wanted to know why. So I identified buildings commonly, but perhaps mistakenly identified as houses, as likely candidates for bars. So I researched the published excavation reports of these so-called houses dating from the classical period, and then carried out analysis on the numbers and shapes of any excavated drinking pottery.
What did you find? What do you think was happening in the average home in ancient Greece?
Well, I think there was an awful lot more trade and commerce than we actually understand. But the first thing I'd like to say is that there was no such thing as an average home in ancient Greece. Literary sources tend to deal with the elites, and it's the elites and citizens of, say, a city like Athens, which therefore receive most of the attention. Athens was an extraordinarily cosmopolitan city, and what might be presumed to be the domestic arrangements of a native might not have worked for a foreigner, and rooms and courtyards would have been used for commercial purposes if the householders so wished, and space could be rented out to traders without the right or the financial resources to own a house of their own. So the use of houses was incredibly diverse in the classical world, and I think we do them a great disservice by studying them and understanding them in a very restricted way that puts one nuclear family within four walls and calls it a house.
I see. So there wasn't this idea that we have now where, one person lives in this house, or perhaps a family lives in this house, and it's just theirs and no one else's.
No, I mean, certainly that would have existed, but, there was far more diversity. I mean, we know that there were apartment buildings in classical Greece as well. Not everybody could afford or even had the right to own property, especially in Athens. But we know that Athens was full of overseas traders, and so these people had to be making use of space somewhere, and I think it's the houses that we should be looking at.
So all this was happening 2,500 years ago, but why are activities like drinking, brothels and gambling so commonly grouped together, and why are they all seen as the seedier indulgences even then?
Yeah, undoubtedly. They undoubtedly were, and I think the key is alcohol. Where there's alcohol, there's loss of inhibition and willpower. And the seedier and perhaps less reputable elements in society would no doubt have gathered where they could take most advantage and make most money. It's a timeless concept, really.
Okay. So could these domestic brothels and pubs, could they have been common elsewhere in the classical world, do you think?
Yes, absolutely. Absolutely. I mean, I look at 5 different sites as part of my doctoral thesis, and they're scattered all over Greece. And I make a case for a building in a site called Olynthus, which is in the north of Greece. And then, of course, Athens is down in the south. But I think absolutely, yes, you would have found these buildings, these activities going on all over Greece and all over the Greek world, certainly.
What about the Roman world as well? Do you think they might have taken any of this on into their cities?
Oh, for drinking and prostitution, unlike the Greek world, we have abundant information from the Roman world. I mean, anybody who's been to Pompeii will be more than familiar with what a Roman bar or a Roman brothel might look like. So, yes, certainly, by the time they reach the Roman world, they become very, very distinct entities, and they're very clear to pick out in the archaeological record. But that was one of the reasons why I was so interested in Greece, because I could understand why it wasn't so obvious in the Greek archaeological records.
So, brothels in the home, Diana?
Well, unfortunately, my flat isn't quite big enough for that kind of party. But now we move away from the delights of ancient brothels and continue with our series of tales about our chemical elements. And this week we welcome back Andrea Seller to hear about the element that led to the birth of spectroscopy, and that's erbium.
A couple of years ago, a colleague popped his head round my door and said, as chemists do, "I'm on the scrounge." It's quite common in chemistry departments. You want to do a quick experiment and just want a smidge of something without having to order a whole bottle. So you ask a friend whether they've got a bit of whatever. "Have you got some erbium oxide?" "Sure," I said. "I've got some up in the lab." And a few minutes later, my friend went off with a small bottle containing a delicate pink-colored powder. A few weeks later, I saw him in the stairwell and asked him how he'd got on with the erbium. "It's amazing stuff. You have to see this," he replied. He pulled out of his pocket a sample vial containing some stunning pink crystals that glinted alluringly. "Wow," I said. You can always impress a chemist with nice crystalline products. "It gets better," he said mysteriously. He beckoned me into a hallway that had recently been refurbished. "Look," he said. As the crystals caught the light from the new fluorescent lamps hanging from the ceiling, the pink color seemed to deepen and brighten up. "Wow," I said again. We moved the crystals back into the sunlight, and the color faded again. And moving the crystals back and forth, they glowed and dimmed in magical fashion. It was a stunning example of the luminescence which is so common amongst the rare earths, of which erbium is a member. The red phosphor in the fluorescent lights must have contained erbium ions, and since the emission wavelength of the phosphor exactly matched the absorption in my friend's crystals, resonant absorption was occurring, causing the magical glow. The rare earths were revealed to the world quite by accident by a Swedish lieutenant and rockhound, Carl Axel Arrhenius, in 1787, in a quarry on the island of Vaxholm in Sweden, where the small town of Ytterby is located. The mineral that Arrhenius had found would lead to the discovery of 16 elements, all of them with remarkably similar properties, and the small village of Ytterby would provide the inspiration for the names of several of them: ytterbium, yttrium, terbium, and the element of this podcast, erbium. Others got names like scandium, holmium, thulium in recognition of the region whence they'd first appeared. For over a century, controversy raged amongst chemists about these elements, and one of the key players in this chemical row was Robert Bunsen, the co-inventor with Gustav Kirchhoff of spectroscopy. Together, they'd had the idea of putting chemical compounds into a flame and analyzing the resulting light with a prism. The spectra they observed proved to be amazing analytical tools. Kirchhoff would use the method to identify elements in the sun. The method rapidly became one of the central pillars of chemistry. But like many others working in the area, Bunsen was intrigued by the faint colors of the rare earths and their remarkable invariance. Erbium compounds, regardless of the partner, the oxide, chloride, fluoride, amide, hydrocarbyls, are almost invariably faint pink. Over a period of 3 long years, Bunsen methodically carried out the hundreds of crystallizations needed to purify the elements, and then meticulously measured and sketched the spark spectra, which contained many sharp bands of varying intensities. It was a spectroscopic tour de force for its time. And at last, in May 1874, Bunsen finished writing his monumental manuscript. With a feeling of relief, he finally headed off to the local pub for lunch. Imagine the poor man's horror when he got back to the lab and the manuscript was gone. A round-bottom flask of water on the desk had focused the spring sunshine from the window and set fire to the entire pile. Years of work reduced to ashes, and after venting his despair in a couple of letters to friends, Bunsen painstakingly redid the work from scratch, laying the foundation of our understanding of the electronic structures of elements such as erbium. We now realize that the valence electrons of erbium, of which there are 11 in its compounds, are buried deep within the core of the atom, and their location makes them remarkably insensitive to the world outside, which is why the colors are so consistent from one compound to the next. But what Bunsen could not know was that there were also spectroscopic bands in the infrared part of the spectrum, and it is these that are what makes erbium so valuable to us today. As you're probably aware, most of our telephone calls and internet data transfers are carried by optical fibers, and these gossamer-thin threads of glass are of a rare optical perfection. But much like light passing through the atmosphere, scattering occurs. Photons of light collide occasionally with the chains of glass in the fiber, and that light is attenuated, limiting the length of fiber one can use. This phenomenon, called Rayleigh scattering, is the same that causes the daytime sky to be blue and sunsets to be red. The shorter the wavelength, the greater the scattering. Erbium light, at 1.55 microns in the near-infrared region of the spectrum, falls right where Rayleigh scattering is at a minimum, but away from where bond vibrations in the glass absorb infrared light. Erbium lasers and amplifiers are therefore the hub around which all of our modern telecommunications revolve. So the next time you phone a friend and say to them, "It's a lovely day, let's go to the park," think erbium. It may only be the 44th most abundant element on our planet, but it punches far above its weight.
So, Robert Bunsen, creator of the Bunsen burner, had his work go up in smoke.
These researchers, they always make a mess, don't they? But that's how science should be done.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientist with Meera and Diana, and this week we're bringing you our favourite interviews and experiments from the show. But now it's time to go back to Chris, Ben and Dave to reveal the perfect way to make tea.
Bob's come back to us. He's actually listening in Canada because he came up with this week's Kitchen Science. Hi, Bob.
Hi.
Now, how's your tea doing? Have you made a cup of tea out there?
Actually, no, I'm not drinking this afternoon.
OK, well, Dave has done your experiment, so let's find out from Dave how it's going. Dave?
Well, I've set up the 3 mugs of tea. 2 of them have got cream in them. One of them I mixed it in well, and the other one I haven't. And there's one which I haven't added the cream to yet.
And the reason for leaving the cream unmixed was because you thought that it might have lots of fat on the surface, which would act a bit like a sort of insulating blanket on the top of the liquid and stop the heat loss.
That was my theory. I'm not entirely sure whether it's worked, but we'll find out. Okay, so at the moment, the temperature of the one without the milk in it yet is 42.5 degrees centigrade. The one with the milk in, well mixed in, is about 43.5, and the one which I didn't mix in is still back to 42.5 degrees centigrade.
So unmixed, no milk in it yet, and it's still just about the same temperature as the one that was...
In fact, the one which I haven't put the milk in yet is actually lower temperature than the one which had the milk cream in to start with.
Okay, so right, let's add the milk.
Add some cream in here. So I've got to measure to make sure that it's fair. I'm not cheating by putting.
Yeah, he's got a sort of egg cup, and he's adding. This is very creamy tea, but at least we know it's very, very rigorous science that's going on here. So
give that a good stir to make sure it's fair. And we've got to wait a little bit for the thermometer to react.
Okay.
Okay, so now adding the cream later, it's down to about 40.8 degrees centigrade. The one where we mix in well is at 43.5. And if we wait a little bit... OK, the reason why the one that was a much worse idea, adding the cream last, is that the amount of heat something's lost is proportional to how hot it is. So the hotter it is, the more heat it's going to lose every second. So if you're going to cool the tea down by adding some milk to it, you want to cool it down as late as possible. So as early as possible. If you're going to take out that energy, you want to do it early, so it's not going to lose much energy because it's colder for the rest of it.
So thinking about this, sort of picturing it, if you drew a sort of graph then of how much energy it's got to give away versus time, then the graph will be really, really steep for the hotter the liquid is. So if you leave it with a high temperature, in other words, no milk in it to start with, it's going to be losing heat to the environment really quickly to start with. And so if you put the milk in it, that brings the temperature down a bit, so the sort of gradient, how hard it's pushing heat out into the environment, is slower, so it's losing heat more slowly, so it should stay warmer for longer than the one that didn't have any milk in it. Yeah, and that was our theory, at least.
And it seems to have worked. And there also seems to be a secondary effect, because the one with the milk in it mixed in fact, the 2 ones with them mixed in seem to have cooled down, ended up at a higher temperature even before we added the milk.
Now, what about your blanket theory of putting the fat on the top and this kept the heat in? Did it work?
It didn't work very well, I think, mostly because the cream was actually denser than the water.
But most of the heat's probably coming out through the ceramic on the cup, isn't it?
There'll be a bit of both. I think you get quite a lot from evaporation from the surface. But both of the 2 ones with milk in seems to have some kind of blanketing effect, because they've actually ended up at, even before we added the milk to the one without milk, they were hotter than it. So they were obviously, it was insulating a bit, but probably had the same effect on both of the 2 cups of tea.
So there you go, Bob. The bottom line is, when you do this, okay, when you get interrupted in your tea break, you have to make your tea and put the milk in before you go off on the interruption. Don't leave it black and then put the milk in after, thinking it's going to be warmer, because it won't be.
So adding milk first does keep it warmer.
Phew, because that's how I always make my tea, so I'm very glad to hear that. And it may be important to savour your tea now and not waste tea bags making new hotter cups, seeing as we're all a bit strapped for cash these days.
Indeed, and speaking of budgeting and the current recession, we have our last highlight, where you visited a trading floor in the City of London to find out how hormones play a role in the performance of our traders, and therefore a role in our economy.
In light of the current economic situation, I've come down to the City of London, to the trading floor of GFI Group. I've come here to find out what underlies the actions taking place here to determine our market. Could human behaviour be playing a vital role in the state of our economy? Well, to help me look into this is John Coates from the Judge Business School at Cambridge University, who's here with me now. Hello, John.
Hello.
So, John, how do the markets really work?
Well, essentially what we're doing in markets are buying and selling assets issued by either private companies or the government. And the job of traders is to buy and sell these securities, and in deciding whether to buy or sell them, they have to make an assessment of the return they're going to make on these assets over the life of holding them and the risk involved.
So you've been looking into the physiology of traders in the City of London. What have you been looking into?
We've been following up a hunch I had when I was working on Wall Street during the dot-com bubble. I was struck by the fact that traders at the time were acting very different from the way they acted before the bubble and after the bubble. They were displaying classic symptoms of mania. They were overconfident, they had racing thoughts, diminished need for sleep, and they were carrying themselves in such an odd way I began to suspect that there was a chemical involved. Second thing I noticed was that women were relatively unaffected by the frenzy surrounding the dot-com bubble. During that time, I was splitting my time between the trading desk and Rockefeller University on the Upper East Side. And there I came across a very, very powerful model that's been tested in a number of different animal species. And I thought this model may be applicable to the financial markets. In this model, it's called the winner effect. Two male animals go into a competition. Their testosterone levels rise in preparation for this competition. The winner comes out of that competition with even higher levels of testosterone, while the loser comes out with lower levels. The winner may go into the next round of competition with an already elevated levels of testosterone, and this can give him an added advantage. It has effects on muscles and the cardiovascular system, but more importantly, it affects his confidence and his appetite for risk. So he goes into this competition with a slight edge. It's what happens in the end game of this model. It's really interesting. As the testosterone levels build up in these male animals, they become overconfident. So, for example, they go out in the open too much. They pick too many fights. They patrol areas that are too large, and they neglect parenting duty. So they suffer an increased rate of predation. And that's exactly what I was observing in traders during the dot-com bubble in New York. They take risks that are, quite frankly, stupid.
So how did you go about actually testing this in city traders?
I got access to a trading floor in the city, and we took salivary steroids from a group of traders over a 2-week period to test that steroids were, in fact, responding to the money they were making and losing in the market, and whether this, in turn, was affecting their trading performance.
And what did you find?
We found that the traders, if they had high testosterone levels in the morning relative to their median levels, they made a lot more money for the rest of the day than they did on days when they had low testosterone.
Well, when most people think of testosterone, they obviously associate it largely with males. So does this then mean that females are relatively unaffected?
Women have about 10% of the testosterone as men, so it's entirely possible that they're not subject to this kind of overconfidence.
But you were also looking into levels of cortisol as well, weren't you?
That's right. In the current environment, that may be the more interesting steroid. When the market turns around and turns into a crash, what can happen is that cortisol, which is a stress hormone, can become elevated in the bodies of traders. And cortisol, if you're exposed to it chronically at high levels for a long period of time, it can have a devastating effect on both the mind and the body. In terms of affecting traders' decisions, what it can do is affect the memories you recall. You tend to recall bad memories, negative precedents. You tend to see risk where maybe there is none. You become fearful, you feel anxiety, and we think that decreases a trader's appetite for risk. So while testosterone is causing people to take too much risk in the bubble, cortisol is causing them to take too little risk in the crash.
So what do you think the current situation is now? Do you think that there are going to be higher levels of cortisol in the traders at the moment?
It's not only how far the market has fallen, but it's how long it's been falling. So these traders have been under stress for almost a year and a half now. Their cortisol levels must be elevated. I'm sure that there's a very good chance it's affecting their decisions.
And you were mentioning that long-term effects of cortisol will have long-lasting effects on their mind's activity. Is this something that companies should think about?
I guess so, yeah. I mean, it's something the Bank of England should be thinking about. Economics is built on the assumption that economic agents are rational, that they respond to price signals. So if you increase the price of something like money by raising interest rates, people will stop buying securities. But they don't in a bubble. On the flip side, during a crash or a depression, they lower interest rates, and economic agents are supposed to respond to that by buying assets so they look more attractive. But if these steroids are reaching such a level in our bodies that we become price insensitive, then monetary policy may no longer work. And in fact, that's what we see.
And so do you think if the banks and the companies understood this physiology a bit more, that they could work together, say, with neuroscientists to try and get out of the economic situation that we're in at the moment?
We're in a bit of a mess at the moment. Cortisol is a hormone that responds not just to like loss or injury, loss being in this case losing money. It also responds more powerfully to situations of novelty, uncertainty, and uncontrollability. And so within banks, I think it's extremely important, although very difficult to do, of course, to create an environment that minimizes the trader's feeling of uncontrollability. Managers think they have to be sort of proactive, as they say in business speak, to show that they're doing something to improve situations. And usually what they're doing is threatening to fire people. And that's exactly the wrong thing you should be doing. We need some positive shock to come into the system of the very sort they're talking about right now, like the bailout package passed in the U.S. last week and being discussed this week in Britain and Europe to break this downward spiral of risk preferences.
That was John Coates from the University of Cambridge. Now, Diana, it really was interesting being on that trading floor because I could just feel a constant buzz and just general stress in the atmosphere.
You weren't tempted to sort of shout, sell, sell, buy, buy or anything while you were there, were you?
Maybe.
Well, we've got to keep our traders calm and in control, I suppose. But at the same time, we need to make sure they don't get off on a testosterone buzz and think they're invincible. Quite a challenge, it seems. Well, now to finish off today's show, we join Dr. Hal and Sideshow Dave again, who've got some more vibrant experiments for us this week.
Vibrant is one way to put it. Here's Laura Soul.
In last week's show, you had a taste of what Dr. Hal and his assistant Dave Campbell showed us when they took time out of their Ministry of Chemistry tour to visit us. Last time it was all about gases. This week, we'll be delving into something a little more dangerous. First up was the silent but deadly phosphorus sun.
This experiment, we're using two of the evil elements. First, we're using the devil's element. We're using white phosphorus. 0.1 gram of that can be a fatal dose if ingested. And if that wasn't bad enough, in here we've got the ultimate oxidant at minus 180. No, liquid oxygen. What we're going to do is we're going to burn white phosphorus in pure oxygen. So what we're going to do is put liquid oxygen into this big light bulb shaped container and let that evaporate off, and that'll make a pure oxygen environment. So in it goes into our container, and 1 mole of any gas occupies 22.4 litres. And I think we've got more than a mole of oxygen in there. Look at it, it's boiling away. And as soon as we put the lid on, what's going to happen is it's going to start evaporating and boiling. Hence, our exhaust pipe is bubbling away quite happily. I think we're nearly there. We've got some oxygen in our environment. And now we need to go to the next danger phase, which is white phosphorus. Now, the reason white phosphorus is so unreasonable is that it quite often catches fire spontaneously in air. So what I need to do is grab my selected piece of phosphorus, and in it goes. And again, it didn't catch fire again, Dave. Isn't that great?
Yes, good. So far, so good.
So far, so good. So Dave's going to heat up this copper rod. So we give it a shove in the right direction. Let's have the lights down, please.
There you go.
And I'm just going to touch the copper rod onto the white phosphorus, and off it goes. And there we have the beautiful phosphorus sun. And the phosphorus is boiling away, burning away, and the beautiful tendrils of phosphorus pentoxide. Curiously, it looks like it should be hot to the touch, but it's not. It's cold to the touch, lots of light, and very little heat.
Beautiful tendrils there. You're showing that really nicely.
The glowing blue jellyfish tendrils of phosphorus oxide really were a sight to behold as they sank gently through the oxygen gas. After that, they moved on to something a little more explosive.
Dave,
yeah.
Chicken though you are, I thought it appropriate that you did your exploding chicken's egg. So pick up the egg and tell us what we're going to do.
What I'm going to do is fill up this egg with hydrogen.
So what we're going to have is a hole at the top and a hole at the bottom.
Correct.
We're going to fill it with hydrogen.
Yes.
And then you're going to light the hydrogen at the top. And it's going to burn off because there's no oxygen in the egg.
That's it, yeah.
But as it burns off, it's going to suck in air from the bottom. And after it gets to about 98% mixture,
then
it'll explode. That's done.
I think it feels okay.
Yeah.
Right, okay.
Right, there we go.
Here we go.
Who's going to light it, Dave? Me or you?
Go on, you light it.
3, 2, 1. Okay, it's lit. Now, we never ever go back to an unexploded egg. So you walk up to it and it blows up in your face.
And just when you're not expecting it.
Oh!
Hydrogen and oxygen really is an explosive mix. However, unsatisfied with that bang, Hal and Dave moved on to bigger things.
Right, well, that was quite good, Dave, and it did explode. But I think we can do better than that, can't we, Dave?
Yes.
Yes, I think that chickens' eggs are for little chickens. But real scientists do it a bit bigger. I think it's time to wheel out the heavy artillery, Dave.
Woohoo, not
the exploding ostrich egg. Da, da, da. So, let's do the experiment again and see if we get a bigger bang with an ostrich egg. So once again, I'm going to fill this with hydrogen, and I need to explain why it's so critical. Because if this goes off and there's oxygen in the egg when I light it, I will suffer a reduction in the number of fingers I have. So we're filling up the egg. So it's critical we have a pure hydrogen environment inside it. And that's why I've got my finger on the top, and that's what the hissing noise is me venting the egg properly. We'll then light it behind those safety screens because this produces lots of jagged shrapnel. All right, lots of it flying around. So it's quite a high hazard experiment. And this produces 130 decibels.
So I think everybody should be put their fingers in the ears.
Yep.
People at home as well, you think? Listen to the radio?
I think radio probably attenuates.
Oh, okay, right, okay. Anyway, I think we're nearly there. Another 5 seconds to go.
5 seconds.
4, 3, 2, 1.
The egg's lit, the shields are together, the flame is on, fingers in your ears, big bang coming up, the hydrogen's burning off with that yellow flame. The flame's going to go from yellow to blue as it gets more oxygenated, and then anything can happen. Fingers in your ears, guys. It's going to go off. Big old bang. Oh, Dave, that's fantastic.
That worked rather well.
Dematerialised. Bye-bye, little egg. Little ostrich. Wow. Bigger bang for your buck with the exploding ostrich egg.
Poor ostrich. We were glad the safety shield held. Next we saw a truly amazing experiment where you can really see chemistry in action.
The barking dog reaction. A classic reaction. The only gaseous phase chemiluminescence. And an example of the diesel effect, all in one experiment.
I can't wait.
I can't wait either. Now, inside this tube I have, which is about 75 centimetres long, we have nitrous oxide, laughing gas. But we're not laughing now, are we, Dave?
Certainly not, no.
And we're going to put in some carbon disulfide, and in common with lots of sulphur compounds, it stinks. So when there's a real smell in the lab, this time it's not Dave, it's the CS2.
There we go.
Right, so CS2's got quite high vapour pressure, so I'm going to mix it all up, and what we're going to do is get a beautiful mixture of CS2 and nitrous oxide in this, and the nitrous is going to oxide the CS2, and we're going to get a lovely blue flash. So, what we're looking out for, let's just summarise once more, is a blue flame slowly going down the tube. That's the chemiluminescence.
Yes.
Which is compressing the residual gas ahead of it. And at some point, depending on the diameter of the tube, you get a diesel explosion, the same as what happens in a diesel engine, which is why they don't need spark plugs.
Quite.
And that's going to explode, pushing out the atmosphere, which is the characteristic woof of the dog. 3, 2, 1. Oh, that was a good one. It burnt down halfway, and then it accelerated at the end, and we've got a beautiful coating of sulphur, brimstone, which is the sulphur from the CS2 that's been reduced.
Not bad, eh?
And that smell that's ripping my lungs apart is some sulphur dioxide, which is produced as a byproduct of the reaction.
There was a beautiful bright glow as the reaction moved down the test tube, releasing light and heat energy, fluorescing like a glow stick. The heat caused the gas in the tube to expand and vibrate violently, creating the awesome bark of the dog. But Dr. Hal decided that just wasn't good enough for the Naked Scientist listeners and really upped his game, from a 70-centimetre test tube to one that was over 2 metres long.
When this goes off, it's 7 foot of angry chemistry, barking dog rage. All right, this is raring to go. And spraying us all with CS2. Okay, so on it goes there. So, 3, 2, 1. The explosion was more than the tube could bear. What happens is the diesel explosion happens there. It's got to go somewhere, but it can't release the pressure up the tube fast enough in this case, so it blew out the side.
And that is one of the many reasons why you should not try this at home. As the glass shards settled to the floor, Hal and Dave brought out their last remaining test tube for the finale, determined to show us how spectacular the big dog can be.
So, for the listeners, I've got a 7-foot test tube, primed and loaded, ready for a big barking dog. 3, 2, 1. Fire in the hole. Wow, what a good one.
It was a good one, that one.
Did you see that big bang, Dave?
Yep.
And can you see the sulphur from the CS2? Look at it. And can you smell the sulphur dioxide?
Oh, gosh, it's marvellous.
I love the smell of sulphur dioxide in the morning.
That really was an ear-splitting woof. The Naked Scientists had great fun with Dr. Hal. If that has whet your appetite for more, go to drhal.co.uk where you can find out what he's up to, plus see experiments that you can try at home. If you want to actually see the experiments that we did with Hal, go to thenakedscientist.com/kitchen science and have a look at our videos.
So lots of explosions there, and I must admit I really enjoyed the barking dog, and it was so powerful that it smashed the glass.
I did enjoy it too, except for the flying glass hurtling towards me, but I did have my safety goggles on, so it was all fine.
Yeah, it really it did hurt my delicate little ears. But sadly, that's it for today's show, and also for our series of highlights from the Naked Scientists. But the good news is our live show is back next week.
Yep, we'll be starting the new series with a Q&A show, and we're primed and ready to answer all those questions you've been waiting all summer to ask. So if you've been dying to know the answer to something, send in your questions to chris@thenakedscientists.com.
And a big thank you to our production staff this week: Tom Simpkins, Ben Valsler, Dave Ansell, Laura Soul and Chris Smith. Thanks for listening. Goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.